Guys, I'm Auryn. I'm the co-founder of Gnosis Guild. We're a Web3 native venture builder. And today I'd like to introduce you to our latest project, Enclave. And its core concept, I guess, encrypted execution environments, or E3s for short, which enable a new class of confidential compute using blockchains and programmable cryptography. So E3s offer this kind of radically different set of trust assumptions to existing solutions like TEs, preferring cryptographic and economic guarantees rather than guarantees rooted in trusted operators and hardware. As a protocol, Enclave coordinates the various cryptographic and economic components along with the actors necessary to enable E3s. Okay. So before I get into the weeds, I think it's important just to understand the broader context in which E3s are designed to operate. Right? So Enclave is specifically designed, specifically intended for computations involving the aggregation of secret state from multiple mutually distrusting parties. I'm not sure how close I should be holding this. So in other words, computations where multiple parties should provide private inputs and need strong guarantees that their input and the intermediate states in the computation will never be revealed, only the output of the computation. So broadly speaking, we see two classes of computation based on the core benefit that they derive from being run in an E3. Sorry. There we go. So the first being those that inherit guarantees of integrity via the reduction of or elimination of information leakage and information asymmetries. So secret ballot systems and sealed bid auctions are two canonical examples where access to voter or bidder information invariably leads to perverse incentives or economically inefficient outcomes. The second class of computations are those intended to generate some insight or output from a data set and can either gain greater access to or reduce liability from that data by not having to take custody of the underlying data in order to produce the insight or output. These are use cases like private data analytics, collaborative research between otherwise competitive institutions, shielded medical research, financial modeling, AI, ML, co-inference, and much more. So encrypted execution environments, E3s, represent this new approach to confidential compute, leveraging a novel combination of programmable cryptography and token economics. E3s provide a secure platform for data processing with cryptographic guarantees of correct execution and strong economic guarantees of privacy. So there's four key technologies that, in combination, enable E3s. These are zero-knowledge proofs, which afford cryptographic guarantees of correct execution of the various phases of an E3, ultimately making each E3 end-to-end verifiable. Fully homomorphic encryption, which enables computation over encrypted data without the need to decrypt the inputs or intermediate states. Multi-party computation, which enables us to broadly distribute trust over a set of node operators who then coordinate to generate secure keys for each E3 and ultimately to decrypt their outputs. And then lastly, blockchain, from which we inherit economic guarantees of correct execution and censorship resistance, along with the substrate on which to enforce our own additional economic guarantees. So we have a handful of important differentiators to other similar projects. E3s are ephemeral, so the encrypted state is only used for the corresponding computation and does not need to remain available. It never needs to be decrypted in future once the output's published. So keys are kind of single use. Each new committee generates a fresh set of keys for each E3, and those keys aren't reused once the output has been published, meaning that there's a kind of limited scope for any compromised keys or any compromised committees. The built-in economics incentives that guarantee security, so MPC parties are bonded, and can suffer penalties for misbehavior, can be slashed with kind of minimal impact to the rest of the system. Developer accessibility, because the heavy part of the computation is run off-chain, it allows us to write the bulk of the program using commonly accessible programming languages like Rust, or at least Rust is our favorite to write in. And then we're encryption scheme agnostic. So Enclave can add support for any FHE scheme that has an implementation of distributed key generation and threshold decryption. Initially, we're supporting BFV and TFHE, but we'll look to add support for other encryption schemes over time. And so along with those three differentiators, there's kind of three key advantages here. One is it's fully open source and publicly auditable. Two, it's modular, compatible with a wide variety of encryption schemes and computing infrastructures, allowing users to initiate their E3s with a combination of trust, cost, and scalability properties that's best suited for their use case. And then decentralized. So it's a broadly distributed set of node operators who are economically staked and incentivized, and they form the kind of root of trust, ensuring sensitive data remains secure. So I want to just help give everyone a mental model of the protocol here. I'll try to use the laser, awesome. So this is, again, mental model of an encrypted execution environment. We're using a hypothetical example here of a healthcare researcher wanting to run some computation over data that's warehoused by a handful of different healthcare providers. It's a kind of multi-phase process here. Worth pointing out that each phase kind of carries a handful of independent ZKPs that, when combined, make the protocol end-to-end verifiable. Process starts here. User makes a request to the protocol to run an E3. That's then going to kick off a sortition process to select a committee of node operators from the globally available pool of staked node operators. They will coordinate to generate a shared public key, publish that key, and then this is the key that each of the data sources is going to encrypt their inputs to. Each data source encrypts their input. Part of that process is generating a handful of proofs around the validity of their ciphertext so that we can push much of the compute kind of to the edge of the computation rather than the core FHE process here. But yeah, they'll encrypt their inputs, publish a commitment to those on chain, and those commitments are inserted into an incremental Merkle tree, giving us a root on chain in which to anchor proofs of correct execution of the core FHE process. That core process then is booted over to a compute provider that was selected by the user. This could take on a number of different forms. Ideally, you're running this in a ZKVM so you can get a cryptographic proof of correct execution of your core logic. But obviously, a ZKVM is going to have some constraints around scalability and cost and may not be appropriate for all use cases. So this is a kind of modular component, and there'll be a handful of different options here that users can select from. So a more optimistically verifiable compute provider. We're currently working with the Arbitrum team on a stylus implementation here. And then we'll also have some kind of Oracle-based and committee-based options here to allow for more kind of economic security and greater scalability as opposed to cryptographic security or cryptographic guarantees around correct execution. In any case, the protocol trusts whatever the selected compute provider publishes as the output of the core FHE process. That's going to trigger then the Cypher node committee to coordinate to decrypt the output and publish that back on chain, or the commitment to that back on chain for consumption by the user. Worth noting there as well that decrypted really just means decrypted from this key and could still be further encrypted to another key controlled by the user. So yeah, I think hopefully that gives everyone a good mental model. Obviously a bunch of moving parts, but this is essentially what Enclave is intended to do, is coordinate these various different components that ultimately, in concert, create an encrypted execution environment. There we go. So I want to finish up by talking about the two beachhead use cases that we're building for, secret ballots and sealed bid auctions. We see these as two ubiquitous organizational and protocol building blocks that will ultimately produce better outcomes with the kind of integrity guarantees afforded by E3s. Auctions, for example, require both transparency and privacy. And leveraging E3s, we can enable sealed bid auctions where only the high bidder and the price they pay are revealed, while the other bidders and bids remain private, or without a trusted auctioneer. So the ability to produce this kind of output without a trusted party with asymmetric access to bid information ensures fairness and integrity and ultimately leads to more capital efficiency in auction-based systems. And auctions are literally everywhere in Web3. Just about every protocol that selects one of several operators competing on price to perform a given function uses an auction under the hood. Solver selection for intents, prover selection for ZK prover networks, block builders in the MEV pipeline, collateral liquidations, just to name a few. If anyone here is working on a protocol that's using auctions under the hood, I'd love to chat after the talk to kind of explore opportunities there. And then, just I guess a couple of key takeaways from this. First is E3s kind of eliminate this reliance on individual trusted operators. Instead, they distribute trust across many bonded node operators to ensure sensitive information is never revealed. And second, E3s allow entities to collaboratively leverage the sensitive data without revealing it to one another, improving integrity, enabling greater access to insights, and reducing liabilities from data custody. All right. So yeah, if you want to dive in further, explore partnership opportunities, or just learn more about Enclave and E3s, then hit me up on Twitter. I'm at Auryn Macmillan, same on Telegram. Follow Enclave, visit us at Notice Guild, or just come say hi after the talk. Thanks.